So today's class, I wanted to move on from talking about electrical attraction and repulsion and positive and negative electrical charges to the description of the electrical force between electrical charges and how we calculate electrical forces between electrical charges. So specifically, we're going to talk about Coulombs Law for the electrical force. We'll compare it to Newton's law for gravity. We'll talk about Superposition Principle for electrical forces. We'll compare that to gravity. And then we'll look at some illustrations or some examples of problems and questions involving calculating electrical forces between electric charges. So that's basically the plan. So just to start with Coulombs Law is an equation, a formula, for the electrical force between a pair of charges. So it's really the building block of calculating, computing forces between electrical charges. So Coulomb was actually, his work was in engineering. So he used to build bridges and things like that. So he was an expert in forces and materials, and he kind of applied that understanding to his hobby or his interest, which was electricity and magnetism. And he developed a method for measuring the electrical force between electrical charges, and by measuring the electrical force between electrical charges, he was able to write down a law, an equation that described the electrical force between electrical charges. I have a little video to show you how he did this. So this shows Coulomb's apparatus. It has two metallic spheres here. One of them is fixed in place. One of them hangs from a wire on this beam here. And when you charge the spheres up with like charge, they repel one another. And he was able to measure the force of repulsion due to the charges, due to the twist of the wire. So let me just show that again. Two spheres, two metal spheres, one fixed in place, one hanging on a beam that's hanging from a thin wire. He applies charge here to the two spheres. They repel one another. He's able to measure the force of repulsion, the tiny force of repulsion, by the twist of the wire. And that's how he developed Coulomb's law that describes the electrical force. So the law, Coulomb's law, incorporates a number of important features that characterize electrical forces. And on this slide, I've just listed those features, and then we'll see the equation itself that kind of puts together all these bits and pieces, all these components of the law. So the first thing is that the force, the electrical force between a pair of charges, decreases with the separation of the charges. So it gets weaker with the separation of the charges in a very special way. It gets weaker as the square of the distance between the charges, so that if you double the distance, then the force will be 4 times smaller. If you triple the distance, the force would be 3 squared. That's 9 times smaller. So it has a very characteristic dependence on the separation between the charges. That's the first point. Second point. The force is in proportion, the strength of the force, size of the force, in proportion to a product of the values of the two charges. So if one or other charges are larger, then you get a corresponding larger force. If one or other of the charges were smaller, you get a corresponding smaller force. So it's the product of the sizes of the two charges that determines the strength of the force. Third point. The forces have a direction. We talked about electrical attraction and repulsion, which is kind of a direction. The forces act along a line, kind of an imaginary line, that's joining the two charges. And that force acts along that line. If the charges are like charges, it'll be a repulsive force along that line, pushing the charges apart. If it's two unlike charges, it'll be an attractive force along that line, attracting the two charges together. So that's the directional properties. So those ideas are kind of all encoded or encapsulated in this slide here. So I've got two pictures and then the equation for Coulombs law. So on the left-hand side here, I'm imagining two like charges. Q1 and Q2 are both positive charges. They're separated by some distance r. Over here, on the left-hand side, I'm imagining two unlike charges, one plus and one minus. Q1 and Q2 are opposite charges here. This line here, is labeled R, is this key piece of geometry. It's the separation. It's the line of separation of the two charges. It has a certain length to it, size to it. That's the distance between the two charges. It has a certain orientation. That's the relative positions of the two charges. So the strength of the force is given by this equation. This is Coulomb's law. The size of the force, Coulomb's law says, is the product of the two charges, the size of the two charges. That's what these vertical lines mean, size of Q1, size of Q2, divided by the square of the distance between them, multiplied by a constant of nature, a constant that characterizes electricity, that sets the scale for all electrical forces. This is called Coulomb's constant. So this is the strength of the force. And then, as I say, the direction of the force is if they're like charges, two pluses, two minuses, it's along that line joining them in the repulsive direction, pushing them apart. If they're two unlike charges, plus minus or minus plus, it's along that line joining the two charges, pulling the two charges together. The forces on the two charges, importantly, obey, you might remember Newton's third law, that when one force acts on a body, another body, an equal and opposite force acts back on the original body. So these forces come in pairs. Whatever force Q1 exerts on Q2, there's an equal and opposite force on Q1 due to Q2. So these forces are in pairs. Just to make some remarks about the law. So this constant K, Coulomb constant, its numerical value is in SI units, 9 times 10 to the 9. So it's a very, very, very big number. And those units are Newton's meter squared over Coulomb squared. If you compare it with the gravitational constant, equivalent thing, gravity, that number was really, really tiny. That number was 6.7 times 10 to the minus 11 Newton meters squared divided by kilograms squared. So these two numbers for electricity and gravity set the scale of the electric and gravitational forces. And these two numbers are telling us that actually electricity is a much, much, much stronger force than gravity. Everyday charges, right? If I'm charging a glass rod or a plastic rod by rubbing it. Everyday charges like that aren't coulombs, don't have the size of coulombs. They have the size of nanocoulombs or maybe microcoulombs. So a coulomb is actually a huge, huge amount of charge. And the experiments we did on Tuesday probably involved nanocoulombs and microcoulombs worth of charge. So that sets that scale. The charges of the elementary particles are microscopic on the scale of Coulomb. So we said that the electron had a charge, negative charge of 1.6 times 10 to the minus 19 coulombs. And the proton had a positive charge of size 1.6 times 10 to the minus 19 coulombs. So they're tiny, tiny, tiny on the scale of a Coulomb. One remark about Coulombs law. So this law applies to the force between a pair of point charges. Just a tiny sort of pin-sized charge in this hand, tiny pin-sized charge in this side hand. It would apply to that situation. Now that's a very limited situation. It's a very important situation because it's a building block of other situations, but it's a very limited situation. We'll see how to expand the horizon of doing calculations of forces between charges later on. But right now, our Coulomb's law is just a force between a pair of point charges. Okay, so I want to look at some illustrations or some examples of Coulomb's law, do some calculations with Coulomb's law. Here's the first one, which is an interesting one. Because I said that electricity is way bigger than gravitational forces. But you might ask, well, how much bigger is it? How much bigger is electricity than gravitational forces? And so if you want to calculate how much bigger it is than gravitational forces, well, how are you going to do that? You might say, well, I'll compare the force between 2 kilogram masses, gravitational force, and 2 1 Coulomb charges. Maybe that's a way of comparing the forces. But the problem with that is that the kilogram and the Coulomb that we're going to compare, well, they're just sort of man-made things. We just invented those units for convenience. There's no reason that they're really special. A better comparison to get a better idea of the relative scale of gravity and electricity is to compare electric and gravitational forces between fundamental particles, say between a pair of protons or a pair of electrons, or an electron and a proton in a hydrogen atom. And so that's what we're going to do. What we're going to do is think of a hydrogen atom, which, as you know, is a combination of an electron and a proton. And here's my picture of a hydrogen atom. The electrons over here on the left-hand side and the protons over here on the right-hand side. They're separated by some distance. And we're going to compare the electrical force between the electron and the proton's charge. I've written those charges here. And we're going to compare the gravitational force between the electron and proton's masses. And I've written those masses here. Now, you probably... So the charges are equal sized, but opposite signs. The masses, there's only positive masses, but they're very different. The protons, like an elephant compared to a mouse, compared to the electrons. So the protons are 1,000 times heavier. Anyway, we'll compare the role of gravity and electricity in a basic atom, hydrogen atom. So I need these numbers. That's why I wrote down the charges and the masses. And I need the gravitational and Coulomb constants. That's why I wrote down those numbers here. So here's Coulomb's law describing the electrical force. Here's gravitational law describing the gravitational force. You notice there's interesting similarities of their forms. They both are inverse square laws. They both either involve the products of the charges that are interacting or the masses that are interacting. And then they both have constants characterizing their scales. So they're patterned in the same way. So if I want to compare, when I say I want to compare electricity to gravity in the hydrogen atom, quantitatively what I mean is I want to calculate the ratio between the electrical force between the charges and the gravitational forces between the masses in the hydrogen atom. So I want to calculate Fe, that's my electrical force, divided by Fg, that's my gravitational force. So that's my goal here. And to do that, all I got to do is fill in my understanding for how electricity works, electrical forces work, that's Coulombs law. Fill in my understanding for how gravitational force works, that's gravitational law. And so I filled those in. Now, what's going to make our task easier is that both those laws were inverse square laws. They varied in the same way depending on the separation between the masses or the charges. And so that inverse square law behavior, that 1 over r squared in Coulombs law, 1 over r squared in gravitational law, that actually cancels out. So I don't need to feed into my comparison of electricity and gravity the separation between the electron and the proton in the hydrogen atom, because it just cancels out in this calculation. So that's handy, that's convenient. And all I've really got to do is calculate the ratio of these numbers. And these are the numbers I wrote down on the last slide. I wrote down the Coulomb constant and the gravitational constant. One was really big, K. One was really small, G. I wrote down the charges of the electron and the proton and the masses of the electron and proton. And if you fill in all those numbers, this is the result. So that result is scale of 10 to the 40, 10 to the 39. That's how much stronger we think of electricity. It's been stronger than gravity by that massive, massive factor, a factor of 10 to the 40. It's not just a bit stronger, a little bit stronger. It's enormously stronger. So you might wonder why then, you know, in everyday life, we notice gravity, we're stuck to the ground, but we're not noticing electricity in everyday life. Why is that? That has to do with the fact that in electricity, there's both positive and negative charges, and there's attraction and repulsion. In gravity, there's only positive masses, and there's only attraction. So, for example, the gravitational force of all the subatomic particles that make up the Earth, all the electrons and protons that make up the Earth, builds up, just accumulates and pulls us down. But the electrical force of all the subatomic particles in the Earth, the electrons and the protons, because the electrons and protons have opposite charges, it cancels out. The repulsion cancels out the attraction. And so that's why we notice gravity in our everyday world. And we notice less electricity in our everyday world. Not because gravity is stronger, it's much weaker, but because of this feature that electricity exhibits both attraction and repulsion, and gravity only exhibits attraction. Okay, let's look at a second example. It's this example here. So, in this situation, I've got two small spheres, two small balls that are hanging from two threads or two strings. And here's an example of this. There's two balls here. They're on these thin cotton threads, and they're hanging there. If I charge those two balls up equally, they will no longer hang vertically. They will kind of defy gravity. They won't hang vertically if under gravity they just hang vertically because gravitational force is pulling them downwards. But if I charge them up, there'll also be an electrical force, a repulsion between them, if I charge them equally. And so that will push them apart. And so if I charge them up, we'll see those two spheres, those two balls, hang at an angle that's a gravity-defying angle that's not vertical. It'll be some degrees away from vertical. I got a video of that. Let me just show you it. So here are the two balls, and like last class, I'm going to get some PVC pipe. I'm going to rub it with cat's fur. I'm going to charge it up, and I'm going to transfer some of that charge to those two balls. Right now, they're hanging vertically downwards. And if I charge them up, now they're not just being pulled down by gravity, but they're also being pushed apart by electricity. And so that they're hanging at an angle that is no longer vertical. Is some number of degrees to the vertical. So we're going to solve this question. Solve this problem. So to make it quantitative, if you look in this question here, the masses of those spheres was 5 grams. They were light. The length of the strings were, in the video, was 40 centimeters. And the angle to the vertical, how many degrees away from vertical they hung, that was 2 degrees. And so, based on this information, we're going to calculate, we know the masses of the two spheres. We're going to calculate what charge I deposited on the two spheres, assuming I deposited equal charge. If you think about it, this little problem, or this little demonstration, is how you might measure charge. You can measure charge by comparing the electrical force with the gravitational force. If you know the masses that determine the gravitational force, you can figure out the charge that's governing the electrical force. So it is a way of measuring, like the electroscope, of measuring electric charge. Okay, so let's try and go ahead and solve this problem. I'm going to try and do it on the, rather than do it on the overheads. So the overheads contain the solution to this problem, if you look at it later. But I'm going to try and go ahead. So the challenge can be my handwriting, and solve it on the document camera here. So I hope this is vaguely legible. As I say, we've got two 5-gram masses. We've got two 40-centimeter long strings. And we've got a 2-degree angle, gravity-defined angle to the vertical. So that's our problem. And we want to find the charges on these masses. So when I read a problem like this, I start thinking about the problem. I start making an image of the problem in my head. And I want to transfer that image to paper, draw it with pen and paper, to make the problem to me concrete, to understand the problem in a concrete way. So I already started it here. So I've drawn the two masses hanging from the two strings on the left and right here. I've indicated the quantities that I know in the problem. So I know the masses of the two spheres, 5 grams on the left and right. I know the lengths of the strings, 40 centimeters on the left and right. And I know the angle that the strings are hanging at. That's 2 degrees. So I'd already started my drawing. But I want to add some things to it. One's just a little bit of geometry. So the little bit of geometry is how far apart, what is the separation of the two spheres as they hang on these two threads? Well, that is just geometry. There's two right-angled triangles here. one on the left, one on the right. We know the hypotenuse of these two triangles is 40 centimeters. If I want the horizontal side of these two triangles, which is opposite the angle, that's the hypotenuse L times sine theta. If I've got two of them, the separation between the two spheres is going to be, I'll call it D, is going to be 2L sine theta. And I already worked this out. This comes out to be 2.8 centimeters. So that wasn't really any physics. That was a little bit of geometry. And as you know, we're not just doing physics in the class. We will do some geometry. We will do some algebra, and so on and so forth. Anyway, that finished my picture, almost. The key thing I wanted to add to the picture is kind of an understanding, a comprehension of what's going on in this situation. So in this situation, with these two balls hanging at 2 degrees, in this situation, the balls are in equilibrium. So they're at rest and they're staying at rest. That's equilibrium. What equilibrium means is that if you add the forces up on either the left-hand or right-hand ball, those forces must add up to 0. The net force, total force, must be 0, because that's what we mean by equilibrium. If the total force, net force is 0, if the body's at rest, it's going to stay at rest. And so, in terms of understanding this problem, the basic concepts, basic notions or ideas are that what's going on is equilibrium, and it's an equilibrium between 3 forces. Let me draw them. There's gravity. I'll call it Fg, downwards. There's electrical repulsion. Electrical force, I call that Fe. It's horizontally, towards the right, on the right-hand ball. And then there's tension. There's a tension in the string. And I'll call that T. And so those are the 3 forces. And those 3 forces add up to 0 total force. And so that's my conceptualization. I don't know if that's really a word, but that's my conceptualization of this problem. That there's equilibrium, and the sum of these 3 forces is 0. Now, when you solve a physics problem, we're solving this problem, I always kind of start with the drawing. That means that I've got a real concrete picture of the physics situation, of what we know and what we don't know. We knew the mass, we didn't know the charge, so on. And it includes my conceptualization of the physics that underlies the solution, this equilibrium. In general, you can turn that concept, that idea, that notion, into a basic equation, kind of a core equation that you can then further develop to solve the problem. So in this particular case, right, the kind of the core equation is that the sum of the forces is 0. So I don't know whether that handwriting is readable, but that's me writing out that the sum, sigma, of the forces acting, say, on the right-hand ball, add up to 0. And so that's the key concept, a key concept. And, you know, there are thousands of equilibrium problems in textbooks, and this one is the core of all of them. So this is very general. I can then expand it a bit to my particular problem. So in my particular problem, I've got a gravitational force, I've got an electrical force, and I've got a tension force. And those are the 3 forces acting on the ball. And those 3 add up to 0. So this is now getting more specific. It's where I'm building in the idea of what forces I have in my particular situation. Okay, so that's really my starting point. So then I start to think about, in a more concrete way, I've got to find the charges on the spheres. find the charges on the spheres, I think I need to know the electrical force between the spheres. To calculate the electrical force, I'm going to have to work my way through the other forces, starting with the gravitational force, which is one I can directly calculate because I know the mass. So that's kind of my plan. But there's another bit to my plan. I'm actually going to expand this equation a little bit, because these forces we all know and love are vectors. They have sizes, they have strengths, magnitudes. I want to rewrite this equilibrium of the forces. I'm going to break it into two halves, into two directions, vertical and horizontal. And that's going to help me. I'm going to break the equilibrium into equilibrium in the horizontal direction, equilibrium in the vertical direction. Let me do that. So I'll write it out and then I'll explain it, because I can't write and think at the same time. So these are my two equations that I'm expanding the equilibrium out into. The top one is equilibrium in the vertical direction, and the bottom one is equilibrium in the horizontal direction. So that's how I've done the expansion. If you think about just vertically, what forces are acting vertically? Well, there's gravity that's pulling downwards. Tension has a component that's upwards. But there's no electricity vertically. And so you see this in this upper equation here. There's just gravity and tension that contribute vertically. And a similar argument for horizontally. That's the second equation. Horizontally, if you look at the picture, electricity acts horizontally. Tension has a component, a portion of it that acts horizontally. But there's no gravity in the horizontal direction. So the second equation only has electricity and tension in it. Now, the amounts of tension in the two equations are determined by the angle of the string and the angle of the tension force. That's theta. So the tension force in the vertical direction, which is the direction next to the angle, that's going to be T cosine theta. That's how we pick that out. And the tension in the horizontal direction, that's down here, that's the piece that's horizontal, opposite the angle, that's T sine theta. So in the vertical direction, we've got gravity downwards, I call that the positive direction, and a portion, T cosine theta, of tension upwards. That's the reason for the minus sign. They add up to 0. In the horizontal direction, we got electric force towards the right, that's the plus sign, and then we got a component of tension, T sine theta, towards the left. And that's the reason for the minus sign. And those add up to 0. And so that's my implementation, my understanding of these forces that are in equilibrium are vectors. And I'm putting that understanding of them being vectors into the equation. Okay. So now I'm going to push that up a bit here. I'm going to execute this master plan of finding electricity. Actually, I'm going to first find gravity force, then find tension force, and then find electrical force. So let's do that. So gravity, we know and love gravity. I've always liked it. Gravitational force on the 5-gram mass is its mass times the acceleration of gravity. Its mass is 5 grams is 5 times 10 to the minus 3 kilograms. Acceleration of gravity is 9.8 meters per second squared. I won't write the numbers in. It'll take me too long, and you won't be able to read it anyway. But the product of those two numbers is 0.049 newtons. And so that's our gravitational force. So that's a sort of confidence building. We're getting going here with the calculation. Now I can actually calculate the tension force. Look at equation number 1 up here. Let me label these. 1, 2. Equation number 1 relates gravity and tension knowing the angle of the string, which we know is 2 degrees. So I can take equation number 1 and I can rearrange it for tension. It would say that the tension is the gravitational force, we know that, divided by is cosine theta. And actually cosine of 2 degrees, if you remember cosines and sines, cosine of 0 is 1. Cosine of 2 degrees is very, very close to 1. It's like 0.999 something. So actually, when you calculate this tension force, it's almost exactly the gravitational force. It's just a tiny fraction smaller, and that fraction smaller is smaller than the number of digits I'm writing down here. So that's the tension force. Okay, now we've got the tension force, I could look at equation number 2. So equation number 2 relates the tension force and the electrical force. If I know the tension force, and again I know the angle of the string, I can calculate the electrical force with equation number 2. It will just be T sine theta. Now, sine of 0 degrees is actually 0. Sine of a small angle like 2 degrees is just a little bit bigger than 0. So now instead of cosine being nearly 1, sine is going to be nearly 0. It's this very small number. And again, I'm not going to fill in the numbers because we can't see what I'm writing anyway. And the answer I calculated was 0.0017 newtons. So I walked through the problem. It's like I know, I'll go outside and walk through this garden of the problem. I've calculated gravity, I've calculated tension, I've calculated, finally, electricity, electrical force. Now my task is simple. It's just applying Coulombs law. Coulombs law relates the separation between the charges, the values of the charges, to the strength of the force. I know the separation between the charges. I know the force, so I can figure out the size of the charges. And so the final step here is I'm going to use Coulombs law. My charges are equal sized and signs, so I'm just going to write Q times Q as Q squared. And here's Coulombs law, where D here is the separation between the charges. So it's the product of the charges times the square of the distance between them times the Coulomb constant, K. And if I rearrange that equation, I can write, so I'm going to rearrange it for the unknown charge Q. If I carry D from the right to from one side to the other side, and then I take a square root, I get this equation here, that the charge on either sphere is equal to the separation between the spheres multiplied by the square root of the force, electrical force divided by the Coulomb constant. If you look at that equation, it makes some sense. For example, if the electrical force was bigger, that equation tells you the charges would be bigger. If the electrical force was smaller, it would tell you that the charges would be smaller. So that's a sensible equation. I'm not going to show it here, but it also makes sense from units. If you were to check the units, so it's obviously coulombs on the left-hand side, you'd find that that funny combination, D times the square root of force over Coulomb constant, that's also coulombs. If you plug in the numbers, 12 nanocoulombs, 12 times 10 to the minus 9 coulombs is the value of that charge. Anyway, that's an example problem involving Coulombs law and working with Coulombs law and working with our understanding of equilibrium of forces and the various forces that are acting to solve for the charge. Any questions on that? This is the first sort of real kind of non-trivial problem that we've done. We stepped over that wall. Okay. again, it's either completely clear or it's completely unclear. And now I've forgot what I'm doing. I want to talk about superposition principle. As I said, the Coulombs law on its own is pretty limited because you can only calculate the force between a pair of point charges. In many situations, you have more complicated situations of more than two charges, and they might not be point charges. And so superposition principle allows you to solve more sophisticated problems. The idea is kind of simple. It's pictured here. So in this picture here, you see three charges. So charge number 1, charge number 2, charge number 3, in these three different colors. And I'm asking you the question of what is the force on the first charge due to the charge 2 and charge 3? The force on the first charge due to the two other charges is simply the sum of their individual forces on the first charge. The force of charge 2 on charge 1 and the force of charge 3 on charge 1. You just got to add them up. Now, adding them up, you have to remember that these forces are vectors. So we all love adding vectors. We have to add these forces as vectors. But superposition just says that the total force due to an assembly of charges is just the sum of the forces due to the individual charges. And it's exactly the same as gravity. You might have met superposition principle when you talked about gravity. Here I'm just showing you visually, pictorially, with force arrows how that works. So look, in whatever this color is here, olive, in this olive color, that's the force due to charge number 2. It must be that it's an unlike charge, opposite charge, because it's attractive. So I draw that force. And then here, this in ketchup, or whatever this color is, this force here, this is the force due to the charge number 3. It must be a like charge because it's repulsive. And so I draw the second force, tail, at the tip of the first force, and then the path from the tail of the first force to the tip of the second force, this other color that I don't know what it is, teal, this is the resulting force. So this is the sum of the forces. You can draw it like this, where I added the force due to charge 3 to the force due to charge 2, or if you have a preference, right, you can add the force due to charge 2 due to the force due to charge 3. That's this way of getting to the same net resulting total force. So that's superposition. So I want to look at an example of superposition. I want to first give you a little quiz on superposition. Again, this doesn't count for credit. We'll start credit next week. Next week you'll start to see, after I give a quiz, I have to go in, and so the quiz will automatically give you 2 or 0, depending on whether you got it wrong or right. But I'll go in and change the zeros to 1s because you get credit for being here. And so that happens after the quizzes because I have to do that by hand because I don't know how to do it automatically. But anyway, that's a long story just to get onto the quiz. So it's about 10:30, isn't it? And so you should see now that I've published this quiz on the superposition principle. And in this quiz on the superposition principle, you asked to imagine these two charges, Q1, Q2, they're like charges. The same, they have in particular, they're both positive charges. That's more important. They're both positive charges. And the questions ask you, where would you put a third positive charge? For the net force on that third charge, due to the two other charges, to be zero. Do you put it to the left, to the right, or in the middle, in the center here? Or is this an impossibility? Is it impossible to make these forces cancel out and get net force of zero? So I'll give you a minute to think about that. I won't give you that long because it's not counting for credit. I won't give you that long because I'm under an enormous stress. That loss of 15 minutes to me at the beginning because of the tornado warning raised my heart rate by a factor of 2. And I'm just trying to cram in as much as I can in a short period of time. Homework number 1 is coming up. It's not for credit, but it's all based on the material in this class. So I want to get through the next example. I will say, though, as I rattle on and lose my time, that I'm posting examples, video examples of me solving problems in the modules directories, because I'll never satisfy you with the number of problems I get through in class. I'll never be able to satisfy your appetite for me working through problems. So I'm going to start throwing them into the modules directory so you can see other problems there. And hopefully they will help you with the homework too. I would definitely recommend do it, although it's not for credit, do this homework, because this homework is like the foundation of all the remaining work on electricity. And so if we kick away the foundation, then the building's going to fall down. So I would do this, definitely do this homework. Okay, well, the answer to this is stick the charge, I've forgotten what I was doing. Stick the charge in the middle, in region B. In region A, if you put the positive charge over to region A, then the forces from the other charges that are repulsive, they're both going to push it over to the left-hand side of the room. If you put it in region C, on the right, both the charges are towards the right, and again, they're repulsive, so they're going to push it towards the right. But if you put it in between the two charges, where they're on either side of charge number 3, well, they're both repelling, but in one case repelling is towards the left, and one case repelling towards the right, and so you can cancel it out. And so it wants to go in that middle region. Everybody okay with that? Okay, I want to do a second quantitative example of superposition principle in the last, this is meant to be the last half an hour that I was going to do this. Now it's the last 10 minutes. So we'll see how this goes. Not half an hour, but close. So here's an interesting problem. I said that matter is made of positive and negative ingredients, and actually equal numbers of positive and negative ingredients. Well, so in matter you've got attractions and repulsions. So why does matter stick together? Why doesn't the attraction be cancelled by the repulsion and everything, like you and I, just fall apart? Matter doesn't fall apart. You and I don't fall apart because the way the charges are arranged in the matter. And so we're going to see why matter sticks together, why it sticks together with this electrical glue by looking at a simple example. So here's what we call a nanocrystal. This is a sodium chloride nanocrystal. It just has 2 sodium ions in magenta here, and it has 2 chlorine ions in lime green here. Chlorine ions are negatively charged in sodium chloride, and the sodium are positively charged. And it forms this sort of arrangement. This is a square. And I call the length of this side A, the length of the horizontal side A here. The distance between these opposite charges, that's by geometry, thanks Pythagoras, as square root of 2a. And the question asks us to calculate the force on this upper left charge due to the other charges, and calculate that force, make it even worse, not as a number, but as an expression in terms of A, the separation between the ions, and Q, the charge, the size of the charges on the ions. And so that's what we're going to do. Okay. So there's several steps to that, and the first one, just like the previous problem on the document camera, is to draw a picture of your mental image of the problem. So my mental image of the problem is I'm focusing on this charge upstairs here on the left. That charge is experiencing three forces. There's a force of attraction to the charge below, there's a force of attraction to the charge on the right, and there's a force of repulsion from the charge over here, the opposite charge. And so here I'm drawing three force arrows. Attraction, attraction, repulsion. I have to add up these three force vectors. I know their directions immediately, right? This is directly downwards, this is directly towards the right, and this is at a 45 degrees along this line separating the centers of these charges. My challenge is going to be to trace the size of these forces through to the size of the resulting force. So what I'm going to do to get myself going, this was my idea. I developed this problem myself, and this was my idea how to go about it. I'm going to define a force called F that has a strength kq squared divided by a squared. Now, the virtue of that is that force of this strength is the strength of this downwards force here, because these charges are separated by A, and the charges have a strength of Q. So this force is, I called it force number 2, for the charge below, has a strength of F. Same thing for this force number 1. There's the attraction to this charge here. Because these charges have size Q and they're separated by A, this also has a strength F. But on the other hand, this force up here, this is weaker. It's weaker because the distance is greater. It's square root of 2 greater. Because the distance is greater by square root of 2, because it's inverse square law for Coulombs Law, the strength of the force is actually simply 2 times smaller. So this third force here is 0.5 F, half an F. And so this is just going to be a handy way of, think of this as a shopping bag, right? It's a handy way of carrying around the Q's and the A's till I get to the end of the question. I pack them into one thing called F because 2 of the forces have that size F and 1 of the forces has the size of half F. And that's going to make it simple for us. My job is to add the 3 forces vectorially, F1 plus F2 plus F3, to make the resulting force, I called it FR for resultant. Okay, so there's 2 kind of components to this problem, the math of solving vector addition problems. So now we're in a math class, right? We did left physics, we went out the back door and went to math. We're going to add up 3 vectors. That's what we've got to do. We know the directions from the picture. We know the sizes from the picture. We've just got to solve the problem of adding them up. How do we do that? In general, we start by breaking the forces into x and y horizontal vertical components. And then, once we've got the individual forces in horizontal components, we can add up the x components to get the total x component, add up the y component, get total y components, and then find the resulting force. So that's basically the plan. This is the first half of that plan. This is finding the x and y components of the individual forces. Force number 1, this is the horizontal one. It's easy to see that its horizontal component is F, because it's all pointing horizontally towards the right, and there is no y component. So that's simple. I didn't need my calculator for that. Similar thing for the second force. It's vertically downwards. So it's easy to see it has no x component. F2x is 0. It just has a y component. Its strength is F, but be careful. It is downwards. I'm going to call that the negative direction. This was towards the right. I called that the positive direction. The one that's a little more complicated, but not too much, is this force here. The one in magenta here has both a x component, this horizontal line here, and a y component. Both of those are non-zero. We can find them because they're the adjacent and the opposite side of this force triangle. We can find the x component with cosine 45 degrees to pick that component out. We can find the vertical component with sine 45 degrees to pick that out. And so that's all I did here. Look, here's the strength of the force, half an F, half an F. Here's the cosine and sine. And here's a plus sign, a minus sign, and a plus sign, because I'm noting that the horizontal component of this force is towards the left. That's the negative direction. The vertical component is up. That's the positive direction. After all that, you get minus 0.35 F horizontally plus 0.35 vertically. Is that okay? I'm sorry. I'm speaking fast. I'm going quickly. Well, I'm just reporting on that. Okay, last step. Now we've got to calculate the resulting force. It's a little hard to see. This is FRX. That's the resulting force's x component. This is FRY, the resulting force's y component. To get those now is simple. We can just add the numbers that correspond to the x components of the individual forces, the numbers that corresponded to the y components of the individual forces. Look at this. I'm just adding F1x, F2x, F3x to get FRX. Adding those up. And I'm doing the same thing for the y component of the forces. When you do that sum, here are the two y components. Sorry, the x and y components of the resulting force. They're 0.65 F towards this is towards the right. They're 0.65 F downwards. You can see that force here. This is in black is a picture of that resulting force. So at this point, all I need to do to get the size, the magnitude of the resulting force, and the direction, the orientation of the resulting force, is to use a little bit of geometry and a little bit of trigonometry.